In today's video, we're going to talk about two common mechanisms in workflow and decision-making systems where we have a requirement to have flexible workflow. So one of the things about workflows that need to be flexible, that aren't strictly speaking pipelines or like middleware that you might see in ASP.NET or Node.js, is we get to a particular place in the workflow, we finish the unit of work, and at the end of it, we need to know what to do next. Where should the execution flow go? Now, in some cases, you can hard code that, right? You can say, well, we're gonna go here next. And in fact, middleware patterns essentially do that, right? At each step of the middleware decides I'm going to handle this or I'm not. And in any case, if it's going to either pass it along to the next step in processing, or it will terminate processing in some other way. But in more complex workflows that have a lot of state, very complicated potential data flows, like we got this message in as part of an order, but in order to figure out the pricing, we have to refer to the order history, or some of the items are at a fixed price, some of the items have different discounting tiers per customer. We might have scenarios where, depending on the item type, we need to have different kinds of shipping pipelines, right? If the thing weighs a couple of metric tons, sticking a stamp on it will probably not make the post office very happy. So in a lot of cases, we're making those decisions based on looking at the state of the message that's being processed, right? If we think about the state of the workflow as being all of the fields and properties that are being passed along through the workflow, or that we can look up in a persistence tier, any of those could be combined to try to figure out where to go next. And in some cases, REIT-style rules engines, right, can do a process called stateful inspection and a rules transition. In some cases, those REIT engines are deterministic. In other words, given the same facts, that they'll always have the same result. In other cases, subtle variations in the state will result in very different outcomes. And sometimes that's appropriate in terms of a workflow, but generally speaking, in a workflow, if we have the same set of facts, we want the outcomes and the steps that we flow through to always be the same. And there are lots of different approaches to this. Some of them are handled by the host of, the runtime of the workflow itself. Others are more ad hoc. In other words, the developers make it, but they basically devolve down to two pretty big groups of patterns. One called finite state machines and the other one called routes. So I wanted to talk about those and the pluses and minuses of each, and some of the consequences of being careful when you're making workflow systems, because they are some of the most complicated day-to-day things that we'll do in business applications. So let's start with finite state machines. And you can read all about this. There's a link to Wikipedia below. I'm not going to try to cover off on all the theory of finite state machines. That's outside the scope of this talk. But I am going to talk about how useful they are in computing what to do next, right? So our scenarios, we're at the end of a workflow step and we need to know where to go next. So in finite state machines, we have the nodes, the circles, and we have the arcs. And if you're in a particular circle, like circle 0, you can see that we can really only go to 1, 5, or 6. And that's represented in the table below that. And so one of the things that factors into the decision making that the computer is going to do is it's only going to go to states that are in the state transition table, that little table down below. It says, I'm here, where am I allowed to go to next? And of course, the decision about what the next value is going to be is some sort of computation, right? But I'm going to check that computation by saying I'm only allowed to go here. Those of you who are developers who are used to using ALM tools like Jira or Visual Studio Team System are used to that with the workflows that accompany tickets or stories, right? We can't go from a new story to a done story, right? There's no direct path to there. But I can go from new to active, and from active I can then put it into an on hold state, or I can put it into an in progress state, and so forth. So if you've had those kind of interactions, you've been interacting with a finite state machine. And for those use cases where you can take a relatively small set of facts and deterministically and exclusively compute what the next possible action is. And by exclusively, I mean that there are no overlaps. I'm going to go from 0 to 1 or 0 to 5 or 0 to 6. And there'll never be a scenario where 5 and 6 are both possible and I coin toss to see which one. In workflow systems, that sort of thing is bad. And so consequently, if we're going to use finite state machines, we have to have a deterministic way of computing what the next step will be based on the facts that are in our datagram. And you can have self-referencing states. In finite state machine lectures that are more focused on math or abstract parts of theoretical computer science, you see scenarios where you could have loops, where 4 could go back to 4 for some reason, where we're going to reprocess over and over again. In the practical use case we're talking about, where we want to force progression through the workflow. And by the way, forcing progression through the workflow also includes the exception case, right? There is orthogonal to this little bubbles and lines diagram, perpendicular to it, and a step that says, this thing just exploded, I'm going to go to the exception case, right? So that's implied in this diagram. And in fact, in all rules engines, right? If this unit of work throws an exception, we're going to go to some special workflow that handles exceptions. That's kind of cool and very dog-foody, right? So just know that if you read up on finite state machines, it is possible to have self-referential steps. 4 goes to 4. But in the real world, you should do everything humanly possible to not have that happen. And we'll talk about why later on. But I can give you a 2-word answer, and it's infinite loops. Infinite loops bad. So the alternative in the decision making is routes. And those of you who have used routing engines for web applications will be pretty comfortable understanding the route concept. Essentially, there's a route table composed of an expression that can be evaluated from the state that it's given. And then based on that, we have a next step determination. And typically the routes are executed in a deterministic order, and the first set of expressions that match result in that step being taken, and the route processing stops and the execution of the designated step starts. In this case, you can see a bunch of different expression types, but they all evaluate to a Boolean of some kind. In other words, if it's false, we're going to fall through to the next route and try to evaluate that. If it's true, we're going to go to the instruction set for the next step and carry on. And at the bottom of the well, we have, wow, this didn't match any of the expressions. I simply don't know what to do with this. And we're going to do our error compensation process. So in this case, rather than being strictly orthogonal to the processing, it's also the error processing is part of the route table. It's the last route. which is, in a web application would be 404. I have no idea what you're talking about. But in a workflow engine, it would be this message or this, processing is incomputable. And typically it goes off into a holding area somewhere. And then, there's generally either an automated or manual or both set of steps that have to kick in to do compensation. So in both cases of finite state machines and routes, they're graph systems, right? If you were to draw these things out, you'd end up with a graph. And what we hope for is a directed graph with an exception processing being orthogonal to the graph, right? But it turns out that both of these things potentially have the ability to have a bunch of horrible things happen to them. Some of them have to do with the decision making we've talked about in this video, and some of them have to do with state corruption. So let's walk through it. Bit shredder. The system disappears messages. This is most commonly the case when we have a persistence tier for our workflow because our workflow runs for a long time. Or worse, we don't have a persistence tier for our workflow and the workflow engine goes down and we lose messages. Either way, right, we have lost some amount of processing. So if it's an order passing through your system, you just lost that order, right? Unless you have a compensation mechanism, your system is basically a bit shredder. If you have a scenario where workflow steps modify the message, especially if they don't persist the original message as a reference, then what you can have happen is your workflows will go to odd places or just make no sense at all. Because the messages have been through enrichment or translation, fold, stapled, and mutilated. And that's really bad. And the best way to deal with that is to have tests, but you can never test enough in messaging systems. And frankly, there's an economic consequence to testing and there's an economic consequence to not testing. And you've got to balance those things. So the other compensation mechanism is to run synthetic transactions through your system and making sure that the common message processing patterns happen in the way that you expect. And we have a whole video on synthetic transactions. The system clones messages, vanilla, vanilla, and vanilla. Call that ice cream clones. And this happens particularly when you have message splitting. You have different parts of the system that process different parts of the message. So for example, in an order, you might have a parallel process that checks the billing, credit limits, things like that. You might have a parallel process that checks the available shipping options. You might have a parallel process that checks your manufacturing schedule to see whether or not the particular thing they ordered can be manufactured in time, et cetera, et cetera. And if you don't have a good rendezvous pattern, or you don't have idempotency, that is, that all of the different splits of the message fundamentally derive from the same identifier, right? Then what you can have is situations where the same message is processed multiple times, and parts of it may not be processed successfully, and other parts of it may be processed unsuccessfully. And the problem is that there really isn't one terminal state, right, where we rendezvous and say, well, okay, it's shippable, their credit history is okay, and they have a need buy on their order date of this date, and we can actually produce the thing that they want 10 days earlier, and allowing for 8 days of shipping by truck, we can satisfy the condition. So be wary of that. Be wary of any time in your workflow you've got parallel processing that you have taken steps to ensure that there's one and only one terminal state for the message. In queue-based systems, which are quite common in workflows, right? Queues are a great place to separate the producers and consumers, which may be working at different rates. There are scenarios where, especially if you're using a topic queue, where you're saying, well, based on this set of facts that are part of the message, this worker process is going to dequeue this message. If you have a scenario where there is nothing that consumes that combination of facts, or it just, the consumer never gets to it, you can have a Flying Dutchman. And in queue stores, typically what happens is that the message falls off the end of the queue. It ages out of the queue and goes to some dead letter store, and then we have compensation. But if the compensation is to put it back on the queue, but there are no consumers that will process the message with that set of facts, right? You can have a Flying Dutchman message. In Through the Outdoor is very similar in the fact that, particularly in route-based systems or in systems with finite state machines, where, remember, the rule is when we compute the next step, there's one and only one right answer. And in route-based systems, the first one that evaluates to true wins, right? If you were to rearrange the finite state machine, or you were to rearrange the routing rules, you can get messages sent to the wrong place. And if we're lucky, what happens when that happens is the unit of work that receives them explodes, throws an exception, and tosses the message into an exception queue. That's the happy case. The unhappy case is it's not that smart, and it attempts to process the order in the wrong way, and we end up shipping a single logo brick on the back of a double semi to the wrong address. And then everyone is confused, and we've wasted a lot of time, money, and resources. So again, synthetic transactions are a good way to manage this and keep an eye on it, but it's a constant problem. Remember, we were talking about finite state machines. We said technically finite state machines are allowed to have self-referencing steps. That is, 4 can go to 4. But that can result in messages getting stuck in our workflow in an infinite loop, something we call a ricochet rabbit. In routing systems, obviously, there's no self-referential possibility, but there is if we pass through a bunch of steps. And so the first time it goes through step 3 and goes to process 3, and then it comes back through having completed process 3 with a new set of facts, and it goes to process 5, and process 5 reprocesses the facts, potentially reverting them, and now the message goes through our routing engine and it's resent to processing step 3. So that message is now in an infinite loop. It's circulating around and around, and you have to do the same sort of detection you would do in Bit Shredder or Flying Dutchman, and among other things, drag a change trail. And if you see a message passing through the same workflow step multiple times, and there isn't a significant state transition between them, in other words, there's no good reason for it to pass through step 3 more than once, then something horrible's happened. So that's a quick overview on some strategies for making workflow decisions in workflow systems and the perils thereof. So how do you choose? If you can possibly make your workflow as much as like middleware as possible, then the chances that you'll have anything but a straight through workflow that is a graph with no branches is pretty good. And there's a reason why web request response patterns and other kinds of manufacturing and processing patterns are deliberately hammered into straight through workflows, is to avoid a lot of the problems we talked about on the last slide. So if you can, do that. But if it's graph-based and you have to choose finite state machines or routes or using a REIT engine, you can certainly do that. But the question then becomes, can you derive a one and only one right answer given the current state and a set of facts? And I'll point out that not being able to compute an answer is not okay, in which case the destination state should be the error state, right? And in fact, in most workflow engines, the right thing to do would be to throw a specific kind of exception that says there is no there. But if you have things that are going to be dynamically changing, right? The shipping rates change on different days or whatever, or we have things that have pricing differentials based on sales or whatever, we may need to do something that's a little more flexible, a router. The other thing is, are the compute steps located together or separate? Is there a central engine that we can use for our finite state machine? Or is, in fact, instead of there being one routing engine, in fact, different parts of the workflow are on different hosts in completely different areas of our ecosystem in our organization, and even potentially outside our organization. in which case, route-based mapping is much more likely. And deferrable execution or near real-time execution. You're using persistence. How do we know how activation, dehydration, and rehydration are going to work? Activation is anything that causes a message to be processed, and dehydration is any time we need to take state and write it to the persistence tier. Rehydration is obviously bringing that back. Is our workflow steps just computing on the data that's sent them, or are they actually doing transformation? If they're actually doing transformation, you might be better off with a route-based system for all its other frailty. There are performance trade-offs. Routing engines are probing, and finite state machines are calculation-based. So depending on the big O of one versus the other in terms of complexity, and whether or not you can get a deterministic answer, these things all fall into place. And of course, can datagrams be split and processed in parallel, as we talked about before? These are all things that you need to think about as a designer and implementer of a workflow system.